The era of bigger being better in artificial intelligence has finally hit a hard wall, but not for the reasons you might think. It turns out that chasing raw model size is actively driving up your bills through hidden inefficiencies like excessive reasoning tokens and failed interaction loops. Recent data reveals a startling truth. In 32% of cases, what looks like the cheaper API option actually costs 28 times more than a premium alternative because developers didn't understand how those models execute logic. The industry isn't just scaling down, it is fundamentally rewriting its architecture toward hybrid, sparse, and edge-native systems where efficiency has become the primary metric for success. When you look at published price lists from major cloud providers or model APIs, they tell a story of linear value that simply does not exist in production reality. A study conducted by researchers at UC Berkeley, Stanford, and the University of Washington analyzed 8 frontier models across 12 diverse tasks ranging from complex math problems to code generation. The results shattered the assumption that lower listed prices always mean lower execution costs. In 32% of model pair comparisons, the cheaper option incurred a higher total cost than its more expensive counterpart. This is not a minor rounding error or an anomaly. It represents a fundamental disconnect between marketing pricing and engineering reality where raw size does not equal efficiency. To understand why this happens, we have to look past the headline price tag and into how these models actually consume compute resources during inference. The hidden fuel guzzlers are what researchers call thinking tokens and interaction turns. When you send a query to a large model designed for heavy reasoning, it may generate hundreds of internal steps before arriving at an answer. In one striking example from the data, Gemini 3 Flash was listed at an 80% discount compared to GPT 5.4. On paper, this seemed like an obvious win for cost-conscious teams. However, in practice, that cheaper model consumed up to 900% more thinking tokens on average and required 10 times more interaction turns to resolve identical queries. The result was a 38% increase in total costs per query despite the aggressive discounting strategy. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This phenomenon exposes a dangerous trap where developers assume they can simply compress their prompts or strip away context to save money without consequence. Research from the University of Science and Technology of China and Huawei Technologies challenges this standard practice, showing that uniform compression often removes critical operational anchors within your system logic. These anchors include essential API calls, validation rules, and structural constraints that guide an agent toward a correct solution. When you strip these away to reduce token count, you do not save money. Instead, you force the AI into costly loops of exploration, debugging, and retries as it tries to recover from missing context. The system enters a state where smaller inputs yield higher execution costs because the model must constantly ask for clarification or attempt failed paths before succeeding. The failure mode here is that we have been optimizing for the wrong variable. For years, the engineering instinct was to feed larger models more data and assume they would solve problems faster with fewer interactions. We assumed that a bigger brain meant better judgment in less time. The reality of modern inference workloads shows that without architectural discipline, size becomes a liability rather than an asset. When you rely solely on brute force scaling, you are paying for capacity you do not need while creating bottlenecks where the model gets stuck in loops. This is why 32% of comparisons showed a price reversal where the cheaper model cost more to run than the expensive one. The difference was not intelligence, it was token efficiency and execution flow. So how do we fix this? The solution identified by recent research is not just about using smaller models, but rather shifting toward architectural designs that prioritize cost-aware skill rewriting and sparse inference. This means selectively preserving high-value structural elements while trimming the fluff from your prompts and workflows. By implementing policies that understand which tokens are critical for operational anchors versus which ones can be safely removed, systems have achieved 7 to 14% reductions in total token costs without sacrificing performance quality. This signals a permanent move away from raw scaling toward hybrid architectures that balance model size with specific hardware constraints like mixture of experts or quantization techniques. This shift requires a fundamental change in how practitioners approach system design judgment. The set it and forget it strategy of deploying the largest available models is now financially unsustainable for most production environments. If you continue to select models based solely on published API price lists or assume that smaller prompts always equal lower costs, your systems will bleed budget through hidden inefficiencies like token bloat and infinite debugging loops. You must start architecting for efficiency by understanding how specific models consume tokens during reasoning phases. This involves auditing your current model selection criteria and considering hybrid inference strategies that leverage sparsity rather than brute force. The engineering rulebook is changing from raw scale to efficiency as the primary metric of success. Developers need to stop chasing size trends and start focusing on how their systems interact with hardware constraints in real-world scenarios. The models that will win are not necessarily the biggest or the cheapest per token, but those designed with awareness of where costs actually accumulate during execution. This is a permanent shift in AI engineering practice driven by economic reality rather than temporary budget cuts. It forces us to build smarter systems that respect both computational limits and financial constraints simultaneously. The path forward involves treating cost as a first-class design parameter alongside accuracy and latency. By adopting these new architectural patterns, you can ensure your AI infrastructure remains viable even when GPU costs spike or inference budgets run dry. The goal is not just to survive the current economic pressure, but to build systems that are inherently more robust and efficient for the long term. This approach transforms cost management from a reactive financial exercise into a proactive engineering discipline that defines the quality of your entire stack. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.